Hi everyone, and welcome back to the MCAT A series of lectures in physics. This lesson will be the first of many lessons to do with electricity. Here, we shall start our discussion by looking at electrostatics, that is, the study of electric charges which are not moving. I shall begin by considering what we mean by charge, before looking at substances which allow charges to easily move, in other words, conductors. Charge conservation will then be considered, which restricts what happens to charges as they move in a system. I will then also look at systems where charges cannot move easily, in other words, insulators. Coulomb's law will then be introduced, which allows us to calculate the electrostatic force between two charged particles. I will then discuss the region around charged particles where that force does act. This is known as the electric field. To help us visualize such fields, I will also introduce electric field lines. The energy associated with electrostatic particles will then be considered, as well as something that is known as electric potential. I'm sure from your everyday lives you have some rough idea of what electric charge is. Whether it be from lightning or from the electric shock you get by walking across a carpet, you know that electric charge is somehow a physical property of matter. More precisely, electric charge is such a property that causes matter to experience a force when it is placed in an electromagnetic field. Such a field I will define more carefully later in this video and in the next video. When discussing charge, we use the letter Q to represent a charge. The unit of charge is one of those 7 base units and it is called a Coulomb. We use the letter capital C to represent a Coulomb. A particular value of charge known as the fundamental unit of charge is of great importance in the MCAT. It has a value of approximately 1.6 multiplied by 10 to the minus 19 coulombs. It is important because it is the charge associated with both an electron and a proton, those charged particles within an atom. Another property of charge you may already know about is to do with their attraction and repulsion. For example, if we have a positive charge and place another positive charge next to it, those particles will move away from each other. This can happen, for example, if a proton is placed next to a proton. These protons will move apart from each other because they are both positively charged. Similarly, if both particles are negatively charged, they will also move away from each other. In general, we say that like charges repel each other. On the other hand, if a positive charge is placed next to a negative charge or vice versa, they will move towards each other. They are attracted to one another. Again, this can be summarized by saying that unlike charges attract each other. These two facts, namely that like charges repel and unlike charges attract, form part of what is known as Coulomb's law, and I will discuss Coulomb's law in full detail later in this video. As I just mentioned, protons and electrons form part of the atom. I'm sure most of you know the structure of the atom already, but just in case, allow me to briefly recap it. In the center of the atom you can find both protons and neutrons. Protons are the positively charged particles and neutrons are the neutral particles, the particles with zero charge. Both protons and neutrons are in the center of the atom. We collectively call the center the nucleus. The nucleus contains both the protons and the neutrons. Outside the nucleus is where we find the electrons, the negatively charged particles. The magnitude of the charge of the electron, as I already mentioned, is E. It is that 1.6 multiplied by 10 to the minus 19 coulombs. More precisely, we say that the charge of the electron is minus E, minus because it is negatively charged. A proton has the exact same magnitude of charge as an electron. It is again 1.6 by 10 to the minus 19 coulombs. What distinguishes a proton from an electron is that a proton is positively charged. The charge of a proton is instead plus E. Overall, if an atom is to be neutral, it must have the same number of protons as electrons. The number of neutrons, however, do not necessarily have to be the same as the number of protons or electrons. The number of neutrons is instead determined by what neutron number makes the atom most stable. This calculation is outside the physics portion of the MCAT. As I already stated, there is something known as conservation of charge within a system. To understand this, let us consider two objects A and B, and let's allow them to physically touch each other. Let's allow there to be physical contact. Anytime there is such physical contact, there can be a transfer of electrons. The reason why it is electrons that can be transferred rather than, say, protons is twofold. Firstly, as I already said, the electrons are on the outside of the atom. Therefore, if you like, they are the easiest to be transferred because they do not have to travel as far as, say, protons or neutrons. Also, electrons are much lighter than protons and neutrons. Roughly speaking, the mass of a proton is approximately 2,000 times that of the mass of an electron. As protons are much heavier, it is more difficult to make them move. Therefore, typically, electricity in general has to do with the movement of electrons, the transfer of electrons. Therefore, let us go back to this example of two objects in physical contact. Let us assume that each object is initially neutral. In other words, it has a net charge of 0. I have represented this by writing 0 in the top right-hand corner for each object. When these two objects are in physical contact, as I mentioned, there can be a net transfer of electrons, either from A to B or from B to A. If we assume that there is electron transfer from A to B, then the resulting situation is as follows. Object A now has less electrons, it now has less negatively charged particles, so therefore it is now overall positive. It is now a positively charged object. Similarly, as object B has gained negative particles, it has now become a negatively charged object. It is negative. Overall, however, the net charge on A and B is 0. Whatever net gain of charge object A has, object B has gained the same with negative charge. Overall, the system of objects A and B is still neutral. A and B together is still a neutral object. This is what is known as charge conservation. Anytime there is a charge transfer between objects, overall the net charge before must be the same as the net charge after. Moving on, I would now like to look at the forces between two particles. As I mentioned, like charges repel and unlike charges attract. Anytime two charged particles are placed next to each other, they will either accelerate away from or towards each other. Anytime there is acceleration, this must be caused by a net force. In other words, charged particles exert a force on each other. There is what is known as an electrostatic force between the particles. To generalize this, let us consider two charges Q1 and Q2. Q1 and Q2 could be, for example, a proton and an electron, or it could be more general. It could be a bunch of protons and an ion, for example, a charged atom. Let us also assume that the initial distance between charges Q1 and Q2 is r. The electrostatic force between both particles is then given as follows. F is equal to a constant K multiplied by the charge of particle 1 multiplied by the charge of particle 2 divided by the distance between the charges squared. This constant K is known as Coulomb's constant. It is roughly equal to 9 multiplied by 10 to the 9 Newton meter squared per Coulomb squared. This unit simply comes about from rearranging this equation for this K. This number may seem quite large, but remember, the charge on an electron or a proton is only 1.6 multiplied by 10 to the minus 19 coulombs. And therefore, in general, unless the distance between the particles is very, very small, the electrostatic force is very small compared to, say, everyday forces. Note also that the form of this equation is quite similar to the gravitational force between two masses. I hope you remember that the gravitational force between two masses m1 and m2 separated by a distance d is given as follows. F is equal to, again, another constant capital G multiplied by the product of the masses divided by the distance between the masses squared. However, unlike the gravitational force, the electrostatic force can be positive or negative. The masses in the gravitational force equation are of course always positive. It doesn't make sense to talk about negative masses. However, it does make sense to talk about negative charges. For example, again, an electron has a negative charge. One or both of these Q1 and Q2s could be negative. If in a calculation the electrostatic force becomes negative, that means that the particles are attracted to each other. This is because the only way to get a negative is by having one and only one of the charges negative. If both charges are negative, you get a negative by a negative, which is plus. If both charges are positive, you get a plus by a plus, which is also plus. Therefore, if you get a negative electrostatic force, you must have a positive and a negative particle. This is therefore two unlike charges, and remember, unlike charges attract. On the other hand, if you get a positive electrostatic force, then the particles are moving away from each other. They are repelled from each other. To help us visualize this electrostatic force, it is a good idea to introduce the concept known as an electric field. Anywhere you have a net electric charge, we say that there is an electric field. This is similar to the way we say that any mass has an associated gravitational field. Electric fields are simply the regions around charged particles where the electrostatic force due to that particle can be exerted or felt. In order to visualize such an electric field, we use what is known as electric field lines. To demonstrate this, let us consider a positively charged particle like a proton. For such a nice smooth spherical object such as this, the electric field lines simply radiate to or from that sphere. By convention, for positively charged particles, we say that the electric field lines radiate outwards. In other words, they point outwards as I've shown here. If instead this particle or these particles were negative, the electric field lines would instead point towards the particles. More precisely, we define the electric field as that electrostatic force per unit charge. In other words, E, the electric field, is the electrostatic force F divided by the charge Q. Typically on the MCAT, you will be using this equation the other way around. You will be given the electric field and the charge and asked to calculate the electrostatic force F. In other words, F is equal to Q multiplied by E. Again, as I stated, these electric fields are produced by the charges themselves. If in this case another particle, for example a negatively charged particle, was placed near this positively charged particle, it would be placed in the electric field of that particle. Because of this, it will experience an electrostatic force due to the presence of this electric field. That force is equal to QE. It is equal to the charge of this particle, and by particle I mean the particle that is in the electric field of this positively charged particle multiplied by the electric field capital E, the electric field of this positively charged particle. Also, introducing such a particle will change the direction and orientation of the electric field lines themselves. As a simple example, let us consider a positively charged particle and a negatively charged particle, both having the same magnitude of charge. In other words, one has a charge of plus Q and the other has a charge of minus Q. In such a situation, the electric field lines look as follows. As I already stated, electric field lines point from positive particles and towards negative particles, and therefore we get the electric field lines seemingly flowing from positive to negative particles. Hence, in this situation, if I introduced another charge, which is assumingly very small compared to these charges, if I place it on one of the electric field lines, that particle would follow that field line. It would move in the direction that that field line was pointing. As I'm sure you can guess, this situation can get very complicated. For example, we can have multiple particles and not just two, or we can have the particles not being so symmetric, not being these spheres that I have drawn. However, for the MCAT, all you need to know is how to draw electric field lines for two particles, two charged particles. I have already given you many examples of potential energy. For example, gravitational potential energy is the energy associated with an object to its position in a gravitational field, for example due to its height from the ground. Elastic potential energy is the energy associated with a stretched spring. In both cases, the energy is called potential energy because there is the potential to do something. If I let go of an object at a height h from the ground, that object will fall. It has the potential to gain speed. Similarly, for a stretched spring, if I also let that go, it will move back towards its original position. The energy associated with charged particles is known as potential energy as well, for similar reasons. For example, let us assume that there is a positively charged particle and I am holding a negatively charged particle. If I then move that negatively charged particle near the positively charged particle, it then has the potential to move towards that positively charged particle if I let it go, if I remove my hand. More generally, if I have a charge or a collection of charges capital Q, and I have in my hand what we call a test charge small q, then the electric potential energy between those particles is as follows. Capital U is equal to, again, this Coulomb constant K, multiplied by that collection of particles capital Q, multiplied again by this test charge Q, divided by the distance between them, or. Again, as with the electrostatic force, the electrical potential energy can be either positive or negative. If both particles have the same magnitude of charge, in other words, if they are both positive or both negative, then the potential energy will be positive, just like for the electrostatic force. If one is positive and one is negative, however, the electrical potential energy will instead be negative. In electrostatics, we also consider another concept which has a name very similar to that of electric potential energy. It is known as simply electric potential. Although their names are very similar, there is a very distinct difference between them. Electrical potential is defined as the ratio of this electrical potential energy to the magnitude of the charge. That is, electrical potential capital V is equal to the electrical potential energy capital U divided by the particle charge. This quantity has units of energy per charge. It is potential energy divided by charge. It has units of joules per coulomb. Again, however, instead of writing joules per coulomb all the time, we define joule per coulomb as a volt. Volt, which we represent by capital V, is the same as joule per coulomb. Why do we bother introducing something so similar? Well, electrical potential energy requires us to have two particles. It requires an initial particle or particles and a test charge. However, electrical potential only requires a particle or a bunch of particles. Recalling the formula for capital Q, the electrical potential energy, we see that for the electrical potential, this test charge Q cancelled. It does not appear in the equation. The electrical potential is simply K capital Q over R. Therefore, a charge or a collection of charges has an electric potential associated with it all by itself. We can calculate the electric potential for a charge or collection of charges at a distance or from those particles without the need of having a test charge. The sign of the electric potential is determined by the sign of the charge capital Q. If capital Q is positive, the electric potential is positive. Similarly, if the charge Q is negative, then the electric potential is also negative. It is also useful to talk about what is known as the potential difference. The usefulness of such a concept will become more clear in a future video when we look at what is known as electric circuits. As electric potential depends on the distance or, we can say that there is a potential difference at two different points in space. For example, if we have a collection of particles capital Q, then we can look at point A, which is 1 meter away from those particles, and point B, which is 2 meters away from those particles. We therefore say there is a potential difference between points A and B. That is, at points A and B, the electric fields and electric forces are different. The potential difference is therefore defined as the potential at point B minus the potential at point A. As we are looking at the same charge, this is simply equal to the potential energy at point B minus the potential energy at point A divided by Q. Instead of writing this difference in potential energies, however, recalling that work done is equal to the change in energy, this is simply equal to the work done divided by Q. What does this work done really mean? Well, I can again consider a test charge small q, and the work done is the work needed to move that test charge through that electric field created by those charges capital Q from point A to point B. A very simplified case is, for example, if the charge capital Q is, for example, a proton. Again, I can consider points A and B as being 1 meters and 2 meters away, and I can consider the test charge as being an electron, a negatively charged particle. The closer I move that electron to the proton, the greater the electrostatic force between the two. Remember, when we have a positive charge and a negative charge, they want to move towards each other. And according to Coulomb's law, F is proportional to 1 over R squared, and therefore the closer these two particles are to each other, the greater the electrostatic force. Therefore, if I placed an electron 1 meter away from a proton, the force is going to be greater than that at 2 meters away. Therefore, if I try to move that electron from being 1 meters away to 2 meters away, I have to do some work. This is because that electron naturally wants to move towards the proton. As there has been some work done, there is therefore a potential difference. The potential difference is simply equal to that work done divided by, in this case, the charge of that electron. So, this was a very brief introduction to the idea of electrostatics. I introduced various different concepts, some of which seemed very abstract, but their uses will become more clear in the next few videos. As always, allow me to finish this video by looking at typical questions that could come up on the MCAT. To begin is a very simple question to do with atomic structure. The question asks us which of the following particles orbits the nucleus of an atom. Is it an electron, a proton, a neutron, or a neutrino? As I discussed, both a proton and a neutron are said to be in the nucleus. They are in the center of the atom. Neutrinos are particles I have not discussed yet, but they will come up when I discuss radioactive decay in a future video. It is the electrons, however, which orbit the nucleus. Those are the particles that are outside the nucleus of the atom. Therefore, the correct answer is option A. This next question has to do with Coulomb's law. We are asked which of the following will lead to the greatest increase in the electrostatic force between charges A and B. Is it increasing the distance between them by a factor of 2, increasing the charge of A by a factor of 3, decreasing the distance between them by a factor of 4, or decreasing the charge of A by a factor of 5? Well, let's recall what Coulomb's law states. Coulomb's law states that the electrostatic force between two charged particles Q1 and Q2 that are separated by a distance r is given as follows. F is equal to the Coulomb constant K multiplied by the product of the charges divided by that separation squared. This means that the electrostatic force is proportional to the size of the charges and inversely proportional to the charge separation squared. Therefore, for option A, if we increase the distance by a factor of 2, we are going to decrease the electrostatic force by a factor of 4. Remember, force is proportional to 1 over r squared. It of course makes sense that the electrostatic force decreases because the particles are now further away from each other. For option B, we are increasing one of the charges by a factor of 3. According to Coulomb's law, increasing one of the charges by a factor of 3 will also increase the electrostatic force by the same factor, that factor of 3. Therefore, we have increased the electrostatic force overall by a factor of 3. If we decrease the particle separation by a factor of 4, then we are going to increase the electrostatic force by a factor of 4 squared, in other words 16. Again, it makes sense that the electrostatic force would increase because the particles are now closer to each other. Finally, for option D, if we decrease the charge of A by a factor of 5, we are going to decrease the electrostatic force by a factor of 5 according to Coulomb's law. Therefore, it is only options B and C which actually cause an increase in the force, and it is option C that causes the greatest increase. Therefore, the correct answer is option C. Finally, we are tested on units of various quantities. We are asked which of the following quantities has units of joules per coulomb. Is it the electric field, the electric potential energy, the electric potential, or the electrostatic force? Well, immediately we know that it can't be B or D. B is a form of energy and therefore has units of joules. D is a type of force and therefore has units of newtons. Newton is not equivalent to joule per coulomb. What about electric field? Well, electric field is defined as force per charge. It has units of newton per coulomb rather than joule per coulomb. This leaves us with electric potential. Remember, electric potential is defined as the potential energy per charge. It is defined as capital U divided by Q. It therefore has units of energy per charge, or joules per coulomb. Therefore, the correct answer is option B. Let us now, as always, recap what we learned in this video. I introduced the concept of charge and described how a charged particle experiences a force in an electric field. I stated that it has a base unit of Coulomb, And I also introduced the idea of the fundamental unit of charge, that is, the unit that both an electron and a proton has, 1.6 multiplied by 10 to the minus 19 coulombs. I also stated that like charges repel and unlike charges attract. This is not a law in itself because it naturally comes from Coulomb's law. I then very briefly recapped atomic structure. I stated that both the proton and the neutron are inside the nucleus of the atom, and the electrons are on the outside orbiting the nucleus. I also stated that both protons and electrons have the same magnitude of charge, but different signs. A proton is positively charged, and an electron is negatively charged. Neutrons, as their name suggests, are neutral particles. They have a net charge of 0. Overall, if an atom is to be considered neutral, it must have the same number of protons as electrons. Two things I did not discuss in this video are what is known as insulators and conductors. Typically, when there is movement of charge, this involves electrons, both because the electrons are on the outside of the atom and because they are the lightest. Insulators are objects or substances which do not allow these electrons to move easily. The reason for this is to do with the chemical structure of those substances, such details which are outside the scope of the physics portion of the MCAT. However, you do need to know common examples of such insulators. Here I have listed several of them: glass, rubber, and air. You know from your everyday lives, for example, that rubber is a very good insulator of electricity. This is why it is used on the outside of, for example, electrical wires. In the middle of that wire instead is what is known as a conductor. A conductor is something that allows the flow of electrons easily. Most metals can be considered good forms of conductors. For example, as I already mentioned, copper as well as aluminum and gold. In electrical wires, the center of the wires are good conductors. They allow the electrical charge to flow easily from the source, e.g. a battery, to the component, e.g. a television. The outside of the wire, as I mentioned, is a cover. It is an insulator, and it is typically made of rubber or plastic. This is because they are good insulators. They do not allow easy transfer of electricity from, for example, the wire to your hand. This allows you to hold the wire without being worried if you're going to get an electrical shock. Then I described what is known as charge conservation or conservation of charge. This is simply the statement that if there is a net transfer of charge between two objects or multiple objects, the overall charge stays the same. Any charge that was transferred from one object to another must be balanced. If one object lost 5 coulombs of charge, the other object must have gained 5 coulombs of charge. I then quantified the electrostatic force between two particles Q1 and Q2. If they are initially separated by a distance r, then the electrostatic force between them is given by the Coulomb constant K multiplied by the product of their charges divided by that separation squared. I then described how any electrical charge has an electric field associated with it. Each charge creates its own field. The magnitude of that field is simply given by the electrostatic force associated with that charge divided by the charge itself. To help us visualize such electric fields, I then introduced electric field lines. I explained how electric field lines allow us to visualize it, but I did not really quantify how they describe both the magnitude and the direction of the electric field. The magnitude is described as follows. The closer electric field lines are to each other, the stronger the electric field is. Therefore, remembering if we just have one particle, for example a proton or an electron, the electric field lines radiate out or in depending on whether that charge is positive or negative. For a positive particle, the lines radiate outwards, whereas for a negative particle, the lines radiate inwards. In both cases, however, the distance between the field lines is increasing with increasing distance from the charge. As they are radiating, then the separation between the field lines is increasing. The direction of the electric field, however, is simply understood to be the direction of the electric field lines. Again, going back to the simple example of just one particle, one charge, if we introduce a second charge known as a test charge and place it on one of the electric field lines, that test charge will accelerate in the direction of the field line, in the direction of that arrow. Based on this fact, we introduced the idea of potential energy. As I just stated, if I place the particle in that field line, that particle has the potential to accelerate. Just like a particle placed above a certain height has the potential to accelerate towards the ground. I also introduced a similar concept known as electric potential, which allows us to quantify the energy associated with the particle that creates the electric field without introducing a test charge. I then ended this lesson by introducing potential difference. Potential difference, as its name suggests, is the difference in potentials at two different points in space. As I discussed, the usefulness of such a concept will become more clear when I talk about electrical circuits in a future video. However, in the next video, I will instead talk about a concept that is closely associated with electricity, that is, magnetism. As always, I hope this video has been useful to you, and I shall see you guys in the next one.